Welcome back to Advent of Code 2025, day 12, the big finale. That's assuming I can finish it this stream. Welcome in, DAJ. Int code problem. There has been a suspicious lack of int codes, so it could be. I assume it'll be the usual system, a part 1 only, and part 2 is to just have completed every previous star. So it seems 9 and 10 were pretty tough for people. 10 looks like it was the hardest, yeah. Okay. That was the one I used Z3 for. Hello, Cheesed Up. Did you go back and finish the ones you didn't get? Yes, I did. I did 3 separate streams yesterday. I finished 10, 9, and 8. Yeah. We all caught up. What's going on here? Is this a game? No, this is programming challenges. And we are on the last one. They're live, so we're waiting for it to just open. Umaro is up to date as well, yeah? I'm guessing he got past that one which I used Z3 for. Which he thought he wouldn't be able to. Maybe he caved in and used another language. Another language. Gotta beat him? Well, okay. There is definitely an advantage to not streaming, though. But then I am using Python and he's using GameMaker. That's an inherent advantage. Alright. Christmas tree farm. You're almost out of time, but there can't be much left to decorate. What language does GameMaker even use? C#? I can't remember. It has its own language, which is similar to C#, I think. But although there are no stairs, elevators, escalators, tunnels, chutes, teleporters, fire poles, or conduits here that would take you deeper into the North Pole base, there is a ventilation duct. You jump in. After bumping around for a few minutes, you emerge into a large, well-lit cavern full of Christmas trees. There are a few elves here frantically decorating before the deadline. They think they'll be able to finish most of the work, but the one thing they're worried about is the presents for all the young elves that live here at the North Pole. It's an ancient tradition to put the presents under the trees, but the elves are worried they won't fit. Cheesed Up, you got big news. I'm in the drama club. My very first ever performance is tomorrow. I'm super excited, but also nervous. Oh, congratulations. What are you performing? The presents come in a few standard but very weird shapes. The shapes and the regions into which they need to fit are all measured in standard units. To be aesthetically pleasing, the presents need to be placed into the regions in a way that follows a standardized 2-dimensional unit grid. You also can't stack presents. It's going to be a bin packing problem. As always, the elves have a summary of the situation. First, it contains a list of the presents' shapes. Oh no. We're going to be playing like Tetris or something. It's a play comprised of a series of skits. Oh, that's cool. Are they like comedy skits? So these... The hash... Alright. We've got a list of the present shapes. It contains the size of the region under each tree, and a list of the number of presents of each shape that need to fit into that region. Alright, so we've got this. First section lists the standard present shapes. Okay. Each shape starts with its index and a colon. Okay. Then the shape is displayed visually. So is it always 3 by 3? Okay. Solution, bigger tree. We're going to need a bigger tree. We've got to be more environmental though. Cut down the presence. The second section lists the regions under the trees. Each line starts with the width and length of the region. And then the rest of the line describes the presents that need to fit into that region by listing the quantity of each shape of present. Oh boy. Okay, so in summary, you're given these presents, so it's the hash, so the dot is just empty space, so the presents look like this. And then for each line here, you've got a separate puzzle. You've got a 4x4 space, and you've got to fit in 2 instances of present 4. And you got to fit them in somehow. And then the next problem, you got to fit 1 instance of problem of present 0, 1 instance of present 2, and 2 and 2. And then the last one you got 12 by 5, and you got to fit these. It's kind of like a, just like a, what's trying to think of the name of the puzzle. No, that's not the one I'm thinking of. Presents can be rotated and flipped as necessary to make them fit in the available space, but they have to always be placed perfectly on the grid. Shapes can't overlap. Well, I mean, it'll be clearer once I actually start. Oh, wow, there's a lot more description. Where was I? Okay, they can be rotated and flipped. So you can take the presents, you can rotate them, you can flip them, you can move them around anywhere, but you've got this big rectangle and you've got to put them in there, and they're not allowed to overlap. The elves need to know how many of the regions can fit the presents listed. In the above example, there are 6 unique presents and 3 regions that need checking. You can fit both presents in this region. Here's one way to do it, using A to represent one present and B to represent the other. So in this example, if you needed to fit 2 copies of this into that space, you could do it like this. A could be like that, and B could be like that, interlocking. The second region, 12 by 5. So they've solved the second one by fitting all the presents in like that. Oh god, okay, well, I think it's going to be a brute forcey type thing. I don't see a clever way of breaking this down into sub-problems, but okay. Is this trying to represent 3D objects on a 2D plane? No, it's fully 2D. The presents are 2D, the plane is 2D. You're just trying to fit those presents in the plane. So A is one present, B is another present, D is another present. You're just trying to, it's just like a Tetris. It's like Tetris. but the presents are not coming down from the sky. You're just kind of putting them anywhere. So the question is, how many... Oh, we've only got 6 presents. 6 present variations. Okay. And we got a whole bunch of problems to solve. Yay. Right. Alright, how do we pause this input? Are they always 3 by 3? That's basically a rule, okay. So... how to get started. Okay, let's first say... Alright, so all the lines towards the end have the letter X in them. So, let's say if X is not in... If can see gift, blow up. Oh, I wish. That could be part 2. No, part 2 is just gonna be... null. If... X... in... line. If X not in line, then we're in the first part. Right. We need presents. And we need a present. So a present, we just kind of append these things into it. So if hash in line or dot in line, we do present dot append line dot strip. So we'd put it into... We're building a present. Are you going to use sterilized fields? What do you mean by that? If the line is empty, then we've finished a present because we've got the 3 things for it. Technically, this doesn't matter how big the present is. I'm in a coding class. It's something I don't quite understand. Sterilized fields. Is that something to do with, like, when people input things in a form, you need to impose restrictions on, like, whether it's a number, whether it's 10 characters long, something like that? I don't know what is meant by sterilized fields, but probably the answer is I'm not going to use them. Alright, if we're in the bottom section, we want... So this is the width and the... The width and the height. No, it's alright, you're not interrupting. Okay, so... tokens equals line dots strip dot split width, height. Alright, cheese, have a good rest. Width, height equals int x for x in tokens, the first token, but we cut off the last character because it has a colon. And then we have to split it on the X character. Okay. Like it's the width and the height. And then these are the indices of the presents. No, this is the counts of the 6 presents. Okay. Present counts equals int x for x in tokens from 1 onwards. Okay, parsing is messy, but let's see what we got. Print presents. No, that doesn't look right. No, that's right, that's right. Yep, that's right. So that's 1 present. That's 1 present. Okay. We should really... Okay. Yeah, I was misinterpreting what the brackets were meaning here. Okay, so that's the presence. Print problems. So we're just wrapping up the problems. Okay. Alright, that feels alright. Okay, so for each problem. So before we proceed, we should probably just compute every possible orientation of a present. So rotate the 4 possible directions, but we also for every possible flip as well. Well, there's just one flip. So you can flip it once and then do all 4 rotations again. So that should be 8 different orientations. Some of which will be the same. And we're not counting how many different solutions we find. We're just like, all we need to do is find one solution. Suppose there could be duplicates. So what we'll have to do is use tuples here. So okay. Present orientations is going to be like a list, and for each present we're going to just make a list of all its possible orientations. So there should be 8, but we'll cut it down if there's duplicates. So for present in presence. So we've got 1 in front of us. NumPy should be able to do this. Let me have a look. NumPy has rot 90. Maybe we use NumPy for this. Okay. We'll use NumPy. It'll just help with the rotations and flipping. So import NumPy as NP. So when we get this present, we can actually input it as np.array. It should just know how to convert it to a present. We just print these. Oh, no, wait. We don't want it like this. Line. Okay. So do we prefer just having 1s and 0s so it's an integer matrix? Yeah, that would make more sense, I think. So this will be 1 if car is hash, else 0. Try that. Okay, there we go. Now, present in presence. Okay, so, okay, so for say temp equals present dot copy. Right, for rots in range 4, or just anonymously say we do present orientations dot append temp, then we rotate temp. So temp equals mp.rot90 temp. So that's all 4 rotations. Now we need to flip it once. Is there a method for that? numpy.flip. Yeah. numpy.flip. Okay. Then flip it. Temp equals numpy.flip temp. And then we just do this again. Also, that is 1. No, we're not putting it there. Putting it in this list here. So after we've done this, we then put that list into here. All right. Let's print that and then print just the first item from that as well. Okay, just print that for now. Alright, printing too much stuff. Get rid of... Okay, no. Okay, print just the first one. Alright, so we've got that. And the next one, let me just do this a bit clearer. For m in print m. So we've got, so basically the diagonal on top, diagonal on the bottom left, right, up, right, and we flip it, and okay, so it coincides. It's fine, I guess. Can we... What happens if I try to put this in a set? Will it remove the duplicates? We can't hash these. NumPy, let me see if there's a quick method for this, otherwise we won't bother. NumPy. List of matrices, remove duplicates. Ah, there's a thing called numpy.unique. Which is exactly what we want. np.unique. Try that. Oh no, that's unique elements. That's not what we want. Wait. Oh. If we say axis equals 0. There we go. Nice! Okay, we got the unique... Oh. Yeah, that's right. We got the unique ones. Alright, so we want... Axis is 0. I'm not sure I understand exactly what axis means here. It's how many dimensions, essentially. Alright, anyway. Oh, that will help. Let me just check this again. Okay. So we've got the presence and all the possible orientations. That's what we want to use. Any other prep we want to do? Alright. So now we want to go through the problems. So we want to say... For... Problems. Alright. So given a problem... So let's create a 0 matrix, numpy.zeros. height. Is that even the right way around? Yeah, okay, so... we want to see... Is this just... I mean, the brute force is not that complex. We just try every possible position, right? So... the interesting thing, though, is that every present touches all four sides. Which means, for example, if the top row was all dots, then that means you could actually put the present with the dots going off the edge of the matrix. But because every present touches all four sides, that's good. That means the 3x3 square has to fully fit inside the matrix. That actually makes things easier to code. So, I need to think for a second. Alright, make this as a method here. Define solve given a matrix to fit them in, let's say, and no. Given a width and height, we'll have to make a new matrix every time we like. Hello, Raiden Heaven. I would think a bit with size, like 4 points, top, left, right, bottom, left, right. That would be a struct. Then I would work with that. Then a method to post that shape on the grid. Yeah. Let's make this method. And given present counts. So when we find a working orientation, we return true immediately. Also, yeah, okay. Ultimately, what do we want to return? We want to, how many of the regions can fit all of the presents listed? So it's just counting how many. Okay. All right. That is the final answer there. Alright, so... Okay, so we've got a... empty matrix. Or we'll just create a new matrix every time. I don't know. We'll see how slow this process is and then think about speed ups afterwards. I honestly have a problem with the wording. I'm dyslexic, so words it's kind of hard to give me the image. But if I see the image, I can figure out how to do it. Yeah, the diagrams certainly helped. Alright. Present counts. Alright, present counts. Let's just go through the present counts. Let's say... I suppose we can do a sort of backtracking type thing. We just have to remember to remove the present. So either that or we just straight up make a matrix every time. I don't think it's going to be that expensive. But we do need to rule out branches where we've already... Yeah, no, we probably should do backtracking. Yeah. Alright, so, do we code it like a search, like a breadth first search type thing? Where a state is the... Yeah, I think so. So a state would be what the board looks like and what remains to be inserted. And a neighbor would be where to insert the precisely the next present in the list. Not any present, but the next one in the list. Because they're commutative, right? So we might as well just narrow the branching. Yeah, let's do that. All right, so we don't do that. Well, that's the start board, I suppose. Present counts is a tuple, right? Yep. Start state then is MP0's present counts. That is the starting state. And the goal state we want to reach is present counts is an empty list, just zeros. So we can do DFS here. We don't really have to do BFS. It doesn't really matter. We can Q equals list containing start state, while Q All right. While Q, we say current state. So current M current present counts equals Q dot pop. So we're given a state and remaining presence to pop on. Do you want to... Well, we can't hash... Can we... We don't want to revisit, but we can't hash MP numpy arrays. We can make a hash method, I suppose, for them. So if I do visited so if we do, you can turn, so if you do this method here, what does that return? It's still an array. But then we could turn that to a tuple, maybe? Let's just call it rep equals that. Rep, I just want to see what this looks like. Did we get that far? Wait, what are we printing? Just this, right? Wait, what? No, this is not what I wanted it to look like. Tuple. No, that you can't just cast it to tuple. Let me see what it looks like. Yeah, so that's a matrix. Or okay, let me try to string. To string. Does it not have that method, or just cast string? It's fine. It's supposed to break. Yeah. I mean, that's fine, isn't it? Okay, fine. So, if rep present counts is in visited, continue. So we just don't want to revisit past ones. All right. And then visited.add that. All right, now we do the actual neighbor logic. So we say the next present count to insert is in here. For I count in enumerate present counts if count not equal to 0 break. So I is the pointer to the present to be added, so the present orientations we want is present orientations I. All right. So for each possible, for P in orients, so for each possible present, for each possible location, so how are we doing this? Just saying, the top left corner of the matrix, the present, where to put that, and then we assume the present's a 3x3, so I can hard code that. Yeah. So for I in range height minus 2. Is that right? If the present was size 1, it would just be height, because we could fit it anywhere. But because it has 2 extra height, then we have to subtract 2. For j in range width -2. So basically we want to insert P at this location. So let's So I guess we want to create a new matrix. So what is... We want to use NumPy matrix slicing or something? Interesting. You can do it like this, so we can say so let's say new m equals current m dot copy new m. So starting from I, to I plus 3, j plus equal P. You just add the matrix like that. Now, if we've resulted in any number increasing greater than 1, so if... How do you check that? You check all... np to all np to all new m less than or equal to 1, or just if not, continue. So if we reach this point, that means we've found a valid place to put it. So we've got the new m and the new, we got to get the new present count. So new present counts equals list of present counts new present counts. We have to subtract 1 from the one we've just inserted, so that was... Oh, we should use a different iter here. Just call it iter. iter minus equal 1. Alright. If... Well, okay, and just tuple it up. If this is all zeros, if all x is 0 for x in new present count, then return true. We've actually found a solution. Don't have to do anything else. Otherwise, we pop this new state on the queue. So queue dot append new m new present counts. And then if we've exhausted every possibility, return false. Alright, that's a... Oh god, that's a mouthful. Is this gonna work? So I've used every possible orientation. It should be not zeros, because if we reach zeros, then we're done. Yeah. Okay, let's print out the solutions if we find them. S equals... Alright, try running it. Two, three, 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 two, three. What? Let me print new M and P. I don't really understand that line. I just copied it. So we've got a big matrix, yeah, and we've got a small shape. We're trying to add that onto the first one. I was just trusting that command. And it crashes. What, on this one? Why we got like 3 shapes here? I don't understand what this means. Looks like we got through a lot of them successfully. New M is a tuple? What? Okay, that's not right. Current M. It shouldn't be a tuple. Wait, what? So when we pop it on the queue... Did I put... yeah, I've written it... Suppose... Creates a view into the relevant section of a large matrix, right? I mean, this looks right, doesn't it? Why have I somehow got a tuple? Am I put... Print... Should I... Oh, is that how you do shape? There we go, okay. Operands could not be broadcast together. What does that mean? So the last... It failed there. We just printed the shapes. That looks pretty normal. Okay, what's my I and J? Maybe we're going off the end of it or something. $39.0. 39, 40, 41. Is... Oh. Should it be -3? It's hot. Alright, let me think. If it was a 1x1 matrix... Should this be -3 then? I don't think... I don't understand this. Operands could not be broadcast together. Yeah, so we're going off the end. That's the problem. Is this right? So... slicing is correct, I think. Is this the wrong way around? Hang on, let me check if MP0's... I bet this is the wrong way around. Hello, Echo Glow. Should really do Advent of Code at some point. It's pretty good. Have you done any of it before? I've done a heck of a lot. Well, I've done all of them so far. Shape. Oh, I think I've got these the wrong way around. That should be height, width, number of rows, number of columns. Okay, stop. Don't print all this stuff. Alright. Let's see if this works. This should work, but it should give the correct answer, but it might be too slow. I don't know. I don't see any way of speeding this up, though. It's like a jigsaw puzzle where you have to try every piece in every possible way. Like, well... Wow. We're stuck on the first line. We've got like hundreds to go. Never done it before. The problems at work usually keep me busy enough. Yeah. Phonetic Flames. What do you think of data science? Data science is... well, it's a very broad field. I've done a fair bit of data science. Both back in university and on the job. Like, I was essentially doing like data science, data analysis for Amazon Prime Video specifically. So I enjoy it. how was working with data analysis. It's quite creative. You don't have to spend as much time maintaining software or fixing it when customers break it. You get to work more on experiments and trying new things and figuring out what customers are doing, why they're doing it, how to give them something better. All right, this is too slow. This whole algorithm is way too slow. Great. Now what? The problem is there's so many repeats here, because this is no good. Should we try printing P and Orients? There's so many possibilities here. That's the problem. So we have so many copies of one present. 25 copies. So if we insert one, then we insert the next one. No. I think we have to think of a different approach here. This is a huge number of presents. Is that actually what that number means? Let me look this up again. Quantity of each shape of present, yeah. That's insane. We have so many repeats. That's the problem. So if we've got we have to insert present 1 47 times. So in this loop, we're taking one instance of present 1, finding a place for it. Then we're taking a second instance of present 1, finding a place for it. But if we had instead put that first present here and that other present here, that's a duplicate of that. So we're basically repeating every possible arrangement of these a billion times. How can I... But they're giving us so many presents to fit in the grid, so... We have to find a whole different approach here. We need to be a bit greedy, like... We know there must be something in the bottom... Alright, breadth first search, we can't use that. Also, should take a sneaky peek at the stats. Or will that discourage us? Let's take a sneaky peek. How many people have solved this? 2,000 people have solved this already. Okay. Alright, I think we've got to just think of something completely different. Nothing springs to mind yet. I mean, let's just check how far we're getting through this. So for P and Orients... Trying every possible place. That's just too many different places. Like, we know there must be a shape in the top left corner. Because if there wasn't, that would just be an empty space, right? So, like, you can break it down and say... that one of the 5 shapes must be in the top left corner. And, like, there's no reason why it would be a bit to the side. Because then you could just push it left and gain more space. So there must be a shape in the top left corner. Can we generalize that? So, with that said... Yeah, let's try that approach instead. So we're always... Let's say instead, we're always trying to place a present as high up as we can, and then as far left as we can. And then the question is just really what shape it is at that point. Then we don't have to worry about all the different possible places we put it, because that's wasting too much time. So change this loop. Also, we're not really using this visited set properly. I won't change anything. I want to see how far we get into this. Print q dot length of q. Interesting, it's hovering around 400. I want to see what happens to it. Does it go back down? How many problems do we have to solve here? $1,000. Alright, the queue is kind of staying the same size because there's always so many to insert. Okay, different approach. We take... Alright, so we get as far as here. So for I in range length, let's say for iter in range length of present counts if present counts iter. So i.e. there's presence that we want to add there. Then we choose the top left place it can be added. Because why wouldn't we? Like, some present needs to go in the top left, so it might as well be. So we might as well just do that. So we take all the possible orientations of that present. All right. For P in orients. So for each possible orientation, we're gonna find the top left space. So we say if current M, so the slice is going to look like this basically. Is all zeros. No, not all zeros. Let me look up numpy extract subregion of matrix as new matrix. So we have to use copy here. Okay. So dot copy. That's what it looks like. The place where we want to insert it. So like M sub, let's call it, is that. So let's say M sub equals that plus P. So it's like we've just slotted it in. I want to see what this looks like. If np dot all M sub is less than or equal to 1, then this is a valid fit, isn't it? So what we can say is this logic here, basically. So we create a new M. We add P into that position. Don't worry about that. New present counts. Remove 1. And if we've found a valid place, if we run out of presents, we've returned true because we've finished. If this is a visited place we visited before, continue. Otherwise, pop that on. So the idea is we're instead always just pushing to the top left space because there's no reason not to, essentially. There's always a present that's going to be in the top left, squashed in at the top left. Otherwise, it would just be empty space. I don't know. Will that work better? Let's see what the numbers end up looking like. So P and orients. Wait, make sure I know what I'm printing here. Okay. Wait. No, I'm not doing this double for loop here. We want to stop as soon as we found a place for it. We don't want to try any other position. So if we've done all this, then found equals true and break. I only want to put it in one place. That's the key, the whole point of this. All right, try that. I just want to see if this actually resolves. We're always trying to stuff things in the top left. I really want to go have lunch now. Can we solve one of these 1,000 problems? This is crazy. Is there some trick, like, we want to figure out how to create squares out of these by putting them together? Like, we can put zeros with twos to make... Oh, that's interesting. Well, not quite that, but... Hmm. No, this isn't gonna work. Oh, it's got to be something like we've got to figure out ways of putting these shapes together. Well, it's been almost a couple of hours and only 2,600 people have solved it, so... Actually, yeah. No, only... Okay, 3,000 people have solved it. So I guess it's a hard one. Yeah, this queue is never gonna empty, is it? But I just want to see roughly what kind of time span we have here. We should check these numbers, so... Oh, we should also run it against the test example. So 41 times 48 is a certain number of spaces. And then if we actually check how many of these get used up... Let me look this up. So 41 times 48 is... 1968. And these ones are like, so it's going to be 47 times 1, 2, 3, 4, 5, 6. It's 27 times 1, 2, 3, 4, 5, 6, 7. 27 times 7. It's 36 times 5. Plus It's 34 times 7. That's 31 times 7. 31 times 7. 32 times 7. 1330. So we've got 1968 spaces, and we've got to fill 1330. So that leaves a lot of gaps. So, like, but then the ones that are impossible, we have to be quite tight. Can't think what to do then. And there's something clever that we're supposed to do with these presents. Well, we should at least make sure we can do the test example. Stop printing stuff. False. Oh my god. We get stuck even on the test example. That's no good. And that's wrong. So it's not even right. Yeah, this isn't quite... Alright, take this out. Still false. Should we go back to what we had before? Iter count in the numerator. Alright, just comment all that out. False. Why is it always false? What's going on here? While Q. Alright, I think it's just completely broken, this method. Visitor.add. Alright. So we've got current M, current present counts. And then we're doing all this. All wait, haven't we? Oh, wow. We added rep present. Oh, no, that's fine. That's the wrong... Okay, so that one should be new present counts. I don't think that's the problem, though. Can we just take that out? Why is it so broken? What the How does it end so quickly? Now that's weird. That means it gets to false. So we don't find any neighbors? Alright, let's check all these things are correct then. So print start state. Stop printing stuff. So just got to add 2 presents. In a 4x4. Shape index 4. Okay. So I'll Q. So current M is that. All right. So we take that state. So print orients, is this right? Yeah. Okay. So P in orients. Print UM. Right, just focus on this problem for now. Okay. So we've put one thing up there. That didn't work. Put it there. Put it there. Put it there. All right. I mean, these two should work, right? We know we should be able to put that. Some of these should work. Wait, look, we've done it. Why? We've fit them together. Why is it not exiting at that point? Ooh, maybe that was the problem. We were actually finding billions of solutions and never actually stopping when we did. If all x equals 0, equals 0 for x in new present counts. New present counts should now be 0. There are less puzzles this year, but the last 4 have seemed to be pretty tough. Yeah, that's true. Alright, something's definitely wrong here. So we printed the new matrix. That's where they've basically combined the two. Okay. New present counts equals list present counts. Oh, we should be calling it current present counts. Oh my god. Okay. Right. Okay, what are we printing? Stop printing so much stuff now. Alright. those back in. True. Now it's stuck. So this one is 12 by 5. I'm trying to put these in. There's too many possibilities. True. Okay, we got true for that one. The answer is true, true. Should be true, true, false. So I reckon we are putting things in too many different places. We should probably always just push wherever we choose to place it. We should always push it up as high as we can and as far to the left as we can, because there's no reason to put it down in the bottom right when you could put it higher. How do we formalize that? Say let's say as soon as we find a place we can put it, break out of this horizontal loop. So we go to the next row. So that cuts out one dimension. That might cut down on the amount of time. Alright, that made that one faster. I feel like there should be a function or whatever to solve this Tetris-like puzzle. Yeah. Alright, I'm gonna go false. Alright, so that's... we know it works for the test input. Great. Let's try it on a big input again, now that I've fixed that major error. Let's see what we get. Oh, we got a true for the first one. We actually solved one. It's the falses that are going to take a long time. If we can get a false to work, then it might just be a case of leaving this running for a long, long time. But is there a better optimization I could have here. So problem is, okay, so if we are put this line back in. So that we're skipping duplicates. So we're always pushing it as far left as we can, but we're not really pushing it as far up as we can. Like, we should say if if j is 0, then there's, so if we've found a place to put it on the far left, then there's no point putting it further down. Like, just stick to that place there. So try that. Can we get one false? Go on, problem 2. I really need to go have lunch. Maybe I leave it running just to see if it actually solves any more of these, but obviously this is not, we can't use this as is. We need to do something more and come back later with another approach. And at least if we can complete a few, at least we don't have to compute those again. We can actually just cut them out of the input. No, but if we can't solve the falses, that's the problem. I think the approach I had before, alright, this thing was sort of yeah, but it wasn't correct. It was missing some cases. Do all the shapes fit together to make one big square? Because generally we have roughly equal numbers here. So if we could actually isolate man. I think I just have to come back later. Let's see, how many people have solved it? Still only about 3,700. Check my leaderboards. Has Romero got it yet? No. Oh, a few people have. Alright, well, yeah, I'll just have to come back later, I guess. Interesting. So that's... So my method might not even be correct. Like, this is an example where you don't actually put something in the top left. Oh. You put something... So the top left... You touch the top left, either the far left wall or something, but you don't put something there. But you could, if this was flipped. The E's would go there. Yeah, the D's and the B's can be pushed up here. So I think you do generally always put something in the top left, but I don't know. Maybe we should make some major hash map that records all the solutions to various rectangles, and then we can split this into rectangles, sub-rectangles, and try to solve them and do something like that. I don't know. We filled like the first few columns, then we know we're trying to solve. Yeah, but it's always going to be jagged. It's never going to be smooth. Can I transform this into A-star search? So right now I'm using depth first search. If I transform it into breadth first search, it wouldn't really change anything. But if I make it A-star search, what would the heuristic be? We're trying to leave minimal gaps. How do we define a gap? Well, maybe that would be... That might actually... be a way forward. If we identify gaps that can never be filled. And A-star search chooses the... No, what? No, A-star is not... That's not how A-star works. No, A-star is the opposite of what we're trying to do. A-star is trying to find the shortest, dirtiest path to get them all in there, but it's not trying to pack them in tightly. Alright, I'll go have lunch and think about it. I'll leave this running in case it actually solves it. That would be interesting. Alright. See you next time.